Hello, so today we are going to do this problem, which is part of August daily challenge. The problem is binary trees with factors. So what we have here is that an array of unique integers, and each integer is strictly greater than 1. And what we want to do is make a binary tree using these integers. And this binary tree has this property where each number can be used any number of times, so we can use it multiple times, but each non-leaf node value should be equal to the product of the values of its children. So each node that is a parent of a node or of other nodes, its value needs to be the product of the values of its children. And we want to return the number of binary trees we can make using this property, and we want to use modulo if the answer is too large. So if you take a look at this example 2, 4, well, we can make, in all cases, we can make a tree of one element where that's a valid binary tree with this property, and so we can have those 2 and 4. 4, you can see its children are 2 and 2. 2 multiplied by 2 is 4, so the property is valid. So this is a valid binary tree. You can see we duplicated 2 here. So yeah, that's valid according to this definition. If we take a look at this one, also we have 2, 4, 5, 10. So each of these separately is a binary tree, and then we have 4, 2, 2. 2 multiplied by 2 is 4. 5, 2, 10. 5 multiplied by 2 is 10, and same thing with reversing the order, right? So you can see we can have the same numbers, but just reversing the order of which is the left and which is the right child. And we can also repeat the numbers if their product is the parent's value, right? And also the values are unique, right? So this is the problem. Now let's see how we can solve it. Okay, so how can we solve this? So what's the property that we have? Well, the property is that the parent value, right? So let's call it num. So this is p.val, or the parent value. That should be equal to its left child value. Okay, actually it's better to use p.val. So if we do p.val, the parent value should be equal to the left value multiplied by right value. So for a number to be considered the root of a binary tree, we need a number that it's divisible by. So let's call it a, such that, so this is such that number is divisible by a, right? So modulo a is equal to 0, and multiplied by what should be, so let's say, and some value x. What is this x value? So this x value should be actually, if the number is divisible by a, it should be just the number divided by a. This is the right value. So with this observation, actually, we can do it in a way where, so why did we do this x here? So one option with the brute force solution is to just do a first loop for a, right? Or call it a1, and this is a2, this is a2. So first loop for a1 in the list of numbers, and then a second loop for a2 in the list of numbers, right? And then a third upper parent loop for number in the list of numbers, right? And then each time we need to check if basically the number is equal to a1 multiplied by a2, right? But this is like too expensive, right? So one way we can think about, okay, how can we get rid of this loop? Well, an easy way to get rid of it is to find a way to obtain it from these two, and just we can check if it's in the array, right? If this value here is in the list of numbers. So that's the first observation. Now the second thing is we can, to check if this is in the list of numbers, if we just use the list, that's expensive, that's O(n). So if we transform the list into a set of numbers, right, or a set of array, then it's easy to check. The check is, so this would be a set for the numbers we have. Then the check is easy. It's an of one operation because we are checking in a set, right? So that's those are the two observations. The second thing is the problem statement says that repetitions are allowed, right? Because in the example we saw, we had 4, 2, 2, right? With 2 duplicated. So what this would mean is that here with the second loop, we don't need to check if the number, if we use the number already or not. Every time we go through all the numbers, right? Now, another thing is, let's say we have a root here, and we have another subtree here, and then we have another subtree here, right? So what we need here, we need to count the number of binary trees, right? Totally everywhere. So let's see, this one was a tree with multiple cases right here, right? And let's say here we had 4 binary trees, and maybe here we had like 3. Okay, and then we find this element has 4, and maybe this element has, let's say, 6, has value 6, and this here has value 2, and this here has value 3 and 2. 3 by 2 is multiplied by 2 is 6, so this is a valid binary tree. So what should be the final result? It should be 1 plus 4 plus 3, right? So basically what I mean by this is we need to check for the node and the product of this, if it's immediate children, but we also need to add our function recursively being called on the children and finding out how many binary trees we have. So it's not just like this operation by checking just the parent. It's taking adding it to the GP of the children, right? And so what does this mean? So since we have subtrees, that means it's easier to do a recursion for this, right? So what we can do here is try, so we have our numbers, list of numbers, right? And we don't know which one, we want to try each one being the root and seeing if that's a valid binary tree. So what this would mean is that we want to return at the end the sum of, let's call our function here maybe count binary trees, right? So we need the sum of count binary trees for number and then for each number in the array, right? And this is basically what this slope is, right? So what's remaining is just doing the rest here. So what should the rest be? So we need to define our function count of BT and see how we can calculate it. So we know that definitely, like with 4, 2, 2, for example, or 4, 2, let's say, each number alone is a binary tree. So we need to start our count with 1 because that node itself at num alone is a binary tree. And so let's say count is equal to 1. And then each number can be a child, right? Because even like, let's say we had 1, 2, 2, right? Then this would be, this here would be a valid binary tree, right? So what this would mean is in our for loop here, we need to do for, let's call it complement in the list of numbers. We want to see if it's a possible solution using the observation that we did earlier here, which is we want to check this, the number is divisible by a, and the number is, the complement is the number divided by a, right? So we want to check if the number that we have here is divisible by this or let's call it a here to match our initial, is divisible by a, and we do have its complement, the number that associates to it. So maybe we call this a1, and we do have number divided by a in our set. Remember the observation that we said where a set array is easier to calculate. So if we have this observation, that means we do have 2 elements where the product is num. At this point, we can count the left and the right children, right? So what we said here is that we need to recurse to add 4 and 3. And so we can do here dp of a1, sorry, not dp, count bt of a1, and count dp of this one. So the two elements that the product is, its product is num, right? Now the other thing is, like in the example that we saw, if we have, let's say, 10 to 5, then 10 to 5 is a valid binary tree, but also 10, 5, 2 is valid, right? So what this would mean is that to get this all of these valid binary trees, we need to multiply, because we can permute for each left and right child. We can do a permutation and just make the left the right and the right the left. So what this would mean is this is multiplied by count of bt of num divided by a2 by a1, right? And then at the we already counted for the number, and so here we can just return count. Okay. Yeah, so I think that's pretty much it. So now we know we need to return this, and this is the function that we do. So 2 observations: just check if the number, if traverse the for a number, this is basically count the binary tree with num as root, right? And so we go through all the numbers and we check, is the number divisible by the one we are looking at? If it is there another element that makes the product equal to the number? So we check if the number divided by a1 is in the set of the elements. If it is, then we count by multiplying the count of each subtree, because we can permute, right? So if this is like subtree 1, this is subtree 2, we can just reverse, right? This is not a we don't have a property that the left has to be smaller than the parent or anything like that, so we can permute without a problem, and so that's why we need to multiply here. Yeah, I hope this is clear. That's pretty much it. The only additional thing is that since we are traversing each array, we probably will do repetitions, right? Because each time we go through the entire array, so we can cache to avoid that, or memorize to avoid this problem. Yeah, so let's code this up and make sure it passes test cases. Okay, so let's see the solution that we just saw in the overview. So yeah, we just need a set of the array, and then we need the mod as described by the problem, but we start the count at 0, and then we go through every element in the array, and we consider it as the root of the binary tree. And so we count the binary trees under it that have it as the root. And so we do that by going through the elements. This is the array. And then we check if the number is divisible by, if num is divisible by the number here. And the number divided by a1 is in the array, which means we have 2 numbers that are where the product is equal to num. And then we count the total of the number of binary trees on the left side multiplied by the number of binary trees on the right side, and or whichever you want to call it, on one side and then on the other side, and then we return the total. And we initialize with 1 because we can construct a binary tree with just num, right? And that's pretty much it. And then at the end we sum all of them up. We do the mod each time just in case the number is too big, and then at the end we return the count mod with the mod. And that's pretty much it. So if we run this, so yeah, this is a1, this is num divided by a1. That's the so if you submit, one thing you can note here is a2 is just num divided by a1, and this gives us that the number is equal to a1 multiplied by a2, right? So we get time limit exception, which is expected because, as I said in the overview, we are doing, each time we are going through all the elements and checking if they create a valid binary tree for us with the property that we have. And so we would have repetitions. So what we can do here is memorize this solution. And so to do that, let's just create a memorization map. And then here, if the number is in it, just return the result that we already calculated before. And then at the end here, in the memorization table, set count, and then return it. And we can submit. Okay, so that passes. Now again, in Python, you actually don't need all of this table. You could just do a cache annotation. So that would be something like, and that will cache it for you. Okay, I'll submit this. Okay, so that passes test cases as well. Yeah, so that's pretty much it for this problem. You can also do this in DP, because you can see here this is pretty much the format. You go through the numbers, go through the arrays, and just get your DP recurrence relation using this formula here. Yeah, and that's also a valid solution. Yeah, so that's pretty much it for this problem. Please like and subscribe, and see you on the next one. Bye.